This question asks us to determine the standard free energy change in joule. So for this question, the first thing we need to do is to determine the anode and cathode and write the half equation. Next, we have to calculate the E naught value by referring this table. We can calculate the E naught value for this question. Next, we have to calculate the standard free energy by put the value into the formula. N is total electron, which is 2, and don't forget to put negative in front of it. And then the Faraday constant is 96.5, and the E naught cell is 0.587. And then we calculate, we will get the negative 113.291 kilojoule per V mole, and we convert it into the joule, which is negative 113.291 joule per V mole. For the next question, we will determine the same thing, which is half equation, and then we will refer to the table to determine the value of the cathode and the E naught, and we will calculate the E naught cell. We will get 1.385 volt. And then we will calculate the standard free energy, which is the total electron is 3. And don't forget also to put the negative in front of it, and then we put the Faraday constant and the E naught cell, and we will get negative 400.958 kilojoule per V mole, and then we will convert it into the joule, which is 400.958 joule per V mole. For the third question, we will determine the half equation to determine the cathode and anode, and then we calculate the E naught cell by referring to the reduction potential table, and we will get negative 1.52 volt. And then we calculate the standard free energy. The total electron is 6, and we put the Faraday constant and also the E naught cell, and we will get the value is 880.08 kilojoule per V mole, and then we will convert it into joule, which is 880.080 joule per V mole. For the last question, we also determine the half equation to determine the cathode and anode, and we also calculate the E naught cell by referring the reduction potential table, and we will get 1.171 volt. And then we calculate the standard free energy. The total electron is 2, and we times Faraday constant and times E naught cell, and we will get negative 226.003 kilojoule per V mole, and then we will convert it into joule, which is negative 226.003 joule per V mole.
Okay, so for activity 4, determine the equilibrium constant for the reaction level at 25 degrees Celsius. So for the first question, we need to determine the anode and cathode. And then we need to find the E naught cell value, which is E naught cathode minus E naught anode. E naught cathode is negative 0.4 minus positive 0.14. And the answer is negative 0.54 volt. Okay, to determine the equilibrium constant, we need to use the Nernst equation, which is E naught cell equals to 0.0592 over number of moles log K. And then rearrange the equation because we want to find the K value.
The atomic radius and ionic radius will decrease. You can see at the atomic and ionic radius strand, the atomic radius and ionic radius will increase going down the group. But as moving across the period, the atomic radius and ionic radius will decrease.
And then we can substitute all the values inside the formula.
Radius and ionic radius will increase going down the group. But as moving across across the period, the atomic radius and ionic radius will decrease. You can see at the atomic and ionic radius trend, the atomic radius and ionic
So the
radius
log
will
K
increase
value
going down the
is
group. But as moving
negative
across the period, the atomic radius and ionic
18.4,
radius
but we
will
want to
decrease.
find value of
You can see
K,
at the
so we need
atomic
to
and
shift
ionic
K in the
radius
calculator,
trend,
and
atomic radius
the
and
final
ionic
answer
radius will
is
increase going down the group. But as moving across the
5.754
period, the
times
atomic radius and
10
ionic
to the
radius
power
will
of
decrease.
negative
You can see
19,
at the
and
atomic
that's the
and
final
ionic radius
answer.
trend, the atomic.
Okay, so for the third question, as usual, we need to determine the anode and cathode, and then we need to find the E naught cell value, which is E naught cathode minus E naught anode, negative 0.14 minus negative 0.337, and the value for E naught cell is positive 0.197 volt. Okay, so to determine the equilibrium constant, we need to use the Nernst equation. So log K equals to 2, which is the number of moles from the above equation, times positive 0.197 over 0.0592. And the log K value is 6.655. And then to find the equilibrium constant, we need to shift log 6.655 in the calculator, and the final answer is 4.519 times 10 to the power of 6, and that is the final answer.
Okay, next for question 2, which is 2Br minus plus Hg2 plus produce Br2 plus 2Hg. Firstly, we write half reaction involved from the equation. And then from the half reaction, we can conclude that anode and cathode, which is Brahman ion is anode and Hg2 plus is cathode. And then we calculate standard solution E cell, which is E naught cell equals to E naught cathode minus E naught anode. From the calculation, we got negative 0.211 volt, and then Nernst equation to calculate equilibrium constant, which is E naught cell equals to 0.0592 per n log K. And then we got K equals to 7.14. Okay, lastly for question 4, which is Ag plus Fe3 plus produce Ag plus Fe2 plus. Okay, firstly we write half reaction involved from the equation. First half reaction, which is Ag and the second one is Fe3 plus ion. Okay, from the half reaction involved, we can conclude that Ag as a anode and Fe3 plus ion is scattered. Next, we calculate the standard potential cell, which is E naught cathode minus E naught anode. In a cell we got negative 0.03 volt, and then we use nerve equation to find equilibrium constant, which is K, which is the formula is E naught cell equals to 0.0592 per n log K. And lastly, we got K equals to 0.3113. This is the final answer.
So hello guys, today we're going to do activity 5. So activity 5 is about electroplating. So if you look at the first question, Roman 1, how long in seconds must a current of 0.4 ampere flow in order to form 8.83 grams of solid silver in an electroplating bath using silver ions as a source of silver? So as you guys can see, I've already written out the what do you call that, the chemical reaction at the electrodes, which is this. Right, so based on this, we can find the answer. So the mass of silver deposited, as the question stated, is 8.83 grams. So we write it down, 8.83 grams. Now we can find the mole of the silver deposited, which is basically mass over molar mass of silver. So we got 8.83 over the molar mass, which gets us 0.082 moles. Right, so based on this equation, so one electron, which equals to 96,500 currents, equals to 1 mole of silver. So since we have 0.082, this equates to about 7913 Cs. So based on this equation, we can put it Q equals to IT. So we're just filling the information, which is Q in this case is 7913, and your amount of current that flows through is 0.4. Sorry. So now we just move around things, and you'll get in seconds 19782.5 seconds, which if we convert it to hours, you will get somewhere around 5.5 hours. So that's for our first question, guys. Moving on to the second question, which is Roman 2. If you guys look at this question, it's basically the same thing as Roman 1, but in this case, the amount of current used and also the amount of silver deposited is different. So the current used this time is 0.5 amperes, and the amount of silver deposited is 2.8 grams. So we just the same thing as we did just now, we'll fill in the informations. So 2.48 grams of silver deposited. So we use the mole formula, which is mole over mass over molar mass. You'll get the amount of moles. So it's 2.48 moles. Then we just substitute, we'll use your calculator, you get your answer of 0.023 moles. So based on this equation, you just substitute 0.023 moles, which gets you about 2219.5 Cs. So substitute the value again, 0.500, your current, which is about 2219.5. Move things around, and you'll get 4439 seconds, which if we convert it to hours, you get 1.23 hours. So that's for the first that's for the Roman 2 question. Right, now moving on to the Roman 3 question, which is calculate the mass of solid copper deposited if the current of 0.8 amperes used under 12 minutes of deposition time. So we first have this formula, Q equals IT. So we'll fill in information first, 0.800 and 12 times 60, because we need to change the minutes to seconds. That's why we have to times 60, and which cancels about 576 Cs. Right. So based on this formula, I've written out these things. This thing over here. So based on this formula, we can compare the stuffs. So now, since you already know the amount of Cs that's used, so if you were to put 576 Cs, which equates to about 2.98 times 10 to the power of negative 3 moles. Right? Moles of copper. So we can find the mass of copper deficit by just using the mole of copper equals to mass of Cu over molar mass of Cu. So we have all the information we need. So it's just 2.98 times 10 negative 3 moles equals to mass over, you have the molar mass of copper, which is 63.546. We just move things around, and the mass of copper ends up to being around 0.19 grams. So the answer as to how much copper is deposited, you guys look at the question. So the amount of copper deposited is 0.19 grams. So that is all for activity 5. Thank you very much, guys.
Hi, my name is Nur Shafika Najwa. Today I will show how to calculate the cell potential for an electrochemical cell using a step-by-step approach. Here's our problem. We have a cell with a zinc electrode as the anode and a solution of Fe2 plus and Fe3 plus ions as the cathode. We are tasked with finding the cell potential E cell at 25 degrees Celsius given the concentrations of the ions. First, we need to identify the half reactions. At the anode, zinc is oxidized to zinc 2 plus, while at the cathode, Fe3 plus is reduced to Fe2 plus. Next, we need to find the standard electrode potentials E0 for these reactions from the sheet table. Based on the table, for anode, the value is negative 0.76 volt, and for cathode, the value is positive 0.77 volt. Overall reaction, we need to multiply the cathode half reaction by 2 because the zinc reaction involves 2 electrons. This ensures the number of electrons gained equals the number of electrons lost. So this is the overall reaction. Then, we need to calculate the standard cell potential. Using the formula for standard cell potential, we substitute the values from the sheet table. The standard cell potential for this reaction is 1.53 volt. Since we are working with non-standard conditions, we will use the Nernst equation to calculate the actual cell potential. In the equation, Q is the reaction quotient, while N is the number of electrons transferred, which is 2. Finally, we substitute the values into the Nernst equation. After calculating step by step, we find the cell potential is approximately 1.51 volt. And there you have it. By following these steps, we have calculated the cell potential for this electrochemical cell. I hope this explanation made the process clear and easy to understand.
Hi, my name is Nur Ain Johanna binti Johan and my matrix number is 227777. Now I will present the standard cell potential and reaction favorability for two electrochemical reactions which include in activity 7. Let's look at the question given. The net reaction that occurs in an electrochemical cell is represented as below. What is the standard potential in a cell for this cell? And is this reaction product favorite or reactant favorite? So this question gives two reactions. So let's solve this. For the first reaction, we have Cu2 plus Ni form Cu and nickel 2 plus. So now let's break it down into first identify the half reactions and their potentials. Cu2 plus is reduced to Cu, and from the electrochemical series, the reduction potential for these half reactions is positive 0.34 volt. And nickel is oxidized to nickel 2 plus, and the reduction potential for this half reaction is negative 0.25 volt. Next, we need to identify the anode and the cathode. So the cathode is where reduction occurs, which is the Cu2 plus forms Cu half reactions, while the anode is where oxidation occurs, which is the nickel form nickel 2 plus half reactions. Then we can use the equation here, which is E naught cell equal to E naught cathode minus E naught anode to calculate the standard cell potential. So standard cell potential, we can get 0.34 minus negative 0.25 and equals to 0.59 volt. So since E naught cell is 0.59 volt is positive, the reaction is product favorite. A positive E naught cell indicates that the reaction is spontaneous under standard conditions. Let's proceed for the second reaction. So we have 2 aluminium 3 plus tin 2 plus forms 2 aluminium and 3 tin 4 plus. So first of all, we need to identify the half reactions and their potential. So tin 4 plus is reduced to tin 2 plus, and the reduction potential for this half reaction is 0.15 volt, while aluminium is oxidized to aluminium 3 plus, and the reduction potential for this half reaction is negative 1.66 volt. So we use the same formula, which is E naught cell is equal to E naught cathode minus E naught anode. So E naught cell we can calculate by 0.15 minus negative 1.66, and we get 1.81 volt. So since E naught cell is equal to 1.81 volt is positive, this reaction is also product favorite. A positive E naught cell means that this reaction is spontaneous under standard conditions too. So to conclude, both reactions have positive standard cell potential, which means they will proceed in the forward direction under standard conditions. Thank you from me.